Swayam Prabha. Digital India. Educated India.
Good morning to all of you. So, today we are going to start a new topic, the drift flux model. Okay. So, till now whatever we had done, we had discussed the different analytical models, and then I had told you that there are usually there are two extreme situations. One is the homogeneous flow model, where we consider that the two fluids are intimately mixed with one another, and we assume it as to be a pseudo fluid with suitable average properties. The next extreme is we assume that the two fluids are completely separated. They may interact, they may not interact at the interface. If you assume that they do not interact at the interface, it is a gross assumption. At times we do it to simplify calculations. Okay. The other extreme is the separated flow model. Okay. Now, the homogeneous flow model, that is also a gross assumption. What we assume that the two fluids, they are flowing, they are intimately mixed and they are flowing as a pseudo fluid, as if none of the phases have a tendency to slip past the other fluid. This is a gross idealization. This can happen only when the mixture velocity is very high, such that the slip velocity is negligible as compared to the mixture velocity. This normally it does not happen, it happens only under extremely idealized conditions for very high phase velocities. Okay. Otherwise, even if it appears that the two fluids, they are totally mixed with one another, it will always happen that there will be a relative velocity between the two phases, because there is always a density difference between them. So, therefore, always the lighter fluid will have a tendency to slip past the heavier one. Okay. So, therefore, what happens? There has to be a slip velocity. Now, if we do not consider this, if we do not incorporate this, then naturally results are bound to be erroneous. So, therefore, an improvement of the homogeneous flow model can be suggested in terms of the incorporating the relative velocity and modifying the expressions of we had obtained for the homogeneous flow model. Now, in that particular case, what we do, we use the concept of drift flux, drift velocity, which we had already defined in our nomenclature chapter. I think in chapter 3 we had already defined those things. So, we will be using the drift flux concept in order to incorporate the concept of relative velocity into the different parameters which we define for the homogeneous flow model. Accordingly, we will be modifying the homogeneous flow equations in order to account for the relative motion between the phases. Now, if you recollect the drift flux model which we had already discussed, the drift flux, the concept of drift flux which we had already discussed, you remember that we had started with the definition of volumetric flux. Volumetric flux is nothing, it is just the volume flow rate per unit cross sectional area, and accordingly just if we take up a single phase fluid, in that case it is just J equals to Q by A, and for the two phases naturally it becomes J1 averaged over the cross sectional area, it is equal to Q1 by A, and J2 this is equal to Q2 by A. And then we had tried to relate the volumetric flux with the local in situ velocity, and these relations they have been given in this particular terms. Okay. And after volumetric flux, the next thing which we defined was the drift velocity and the drift flux. So, the drift flux, how did we define it? We had defined the drift flux in something of this particular term, the drift flux of component 2 with respect to component 1. This was defined as alpha u2 minus j, or the j2 phase, if we consider the two phase mixture in this particular case, where we defined it as the velocity of one fluid with respect to a observer moving at the maximum, or rather sorry, moving at the average velocity. In that particular way we had defined, and then what we had done, we had done several particularly important derivations, and finally we had arrived at two important equations. One was a symmetric equation J21 equals to minus J12, which you must be remembering. The other was J21, it was alpha into 1 minus alpha U21. So, these were the two final equations that we had obtained when we were discussing the concepts of volumetric flux, drift velocity and drift flux towards the end of our nomenclature chapter. Now, from whatever we have defined during that time, we can see that we come across certain interesting equations in this particular case. For example, we had, as I had written down in the previous class, the derivations are more or less done in this PPT, but we will be deriving them, and then you can refer to the PPT as and when it is required. So, the starting from the basic definitions, please remember always we will be starting from the basic definitions and then we will be proceeding. So, what does this give us? This gives us alpha into U2 minus J1 plus J2, right. Alpha also U2 also we can substitute it in terms of J2, and we get a equation something of this sort. Agreed? We have just substituted J and U2 in terms of component fluxes J1 and J2. Okay. So, from here what do we get? J2 minus J1 alpha minus J2 alpha equals J21, or in other words we can get it as, in fact without doing so much also I could have got it, to be very honest. From here itself I could have got it. It is J21 equals to J2 minus alpha J. Okay. Same thing I could have, I can get from this particular thing also. It is J2 minus alpha J1 plus J2. It is not required to do it in this particular way. I could directly from, I wanted to derive one other equation. So, I had started this way anyhow. So, I can get, we can very well get this particular equation. Now, from this particular equation, what is the value of alpha that you get? Alpha equal to, just derive the value of alpha from this particular expression and see what you get. Alpha will be equal to J2 minus J21 by J, right. Now, what is the homogeneous value alpha, can you tell me? For homogeneous value alpha equals to beta. So, therefore, the homogeneous value alpha is, how can we express the homogeneous value alpha, alpha obtained from the homogeneous flow theory? Yes, it is just the input flow rate of phase 2 divided by the total input flow rate, is not it? Alpha equals to beta. For the homogeneous flow theory, we get this equal to Q2, and this is nothing but equal to J2 by J1 plus J2. Is not it, for the homogeneous flow theory? Yes or no? We get this from the homogeneous flow theory. Agreed? So, therefore, from the homogeneous flow theory, alpha equals to J2 by J, is not it? So, this we can write it down as J2 by J into 1 minus J2 1 by J2, right. Or this can be written as alpha homogeneous into 1 minus J2 1 by J2. So, therefore, what do we find? Just by incorporating the concept of drift flux, what did we do? We have just modified the homogeneous flow value alpha, we have just modified this by multiplying it with a correction factor which is a function of J21. So, basically we find that the alpha which has been obtained from the drift flux model, that is equal to alpha homogeneous into some sort of a correction factor, where this correction factor, this is a function of the correction factor is a function of J21, is not it? So, therefore, basically what has the drift flux model done then? It has simply modified the homogeneous alpha value by incorporating the relative motion between the phases. So, that now we can expect that since the relative motion has been considered, we can expect to get a more accurate value of the void fraction under practical situations. Agreed with me? Now, we will find that similarly what this drift flux model does is it modifies all the mixture properties obtained from the homogeneous flow theory by incorporating a correction factor which is a function of J21 by J2 or J21 by J1 or J21 by J as the case may be, but it simply considers this particular relative motion in the form of drift flux, and by incorporating this drift flux in the expressions of the different parameters, say the different parameters can include alpha which you have already seen. We will be seeing shortly how it modifies the expression of the mixture density rho Tp, how it modifies the expression of u1, u2, even it modifies the expressions of momentum flux, kinetic energy flux, everything. It modifies all the expressions which we had obtained from the homogeneous flow theory by either adding or multiplying a particular correction term, where this particular correction term, it is a function of J21, the drift flux model, the drift flux which we had derived. Agreed? So, in this particular way, we find that the drift flux model, it attempts to modify or improve the predictions of the homogeneous flow model just by incorporating a correction factor either as a multiplicative or an additive term, and this particular term is invariably a function of drift flux J21 or J12 as the case may be. Agreed? So, this is basically what it does. How it modifies the concept, or rather the expression obtained for alpha homogeneous is by this particular expression. We can simply multiply alpha homogeneous with 1 minus J21 by J2 and we get the corrected alpha for the actual situation. Similar way, if we take up say the density, the mixture density rho Tp, we know what is the mixture density. It was alpha rho 2 plus 1 minus alpha rho 1. Agreed? From the homogeneous flow theory, we know alpha equals to beta, isn't it? So, for that particular case, it is simply J2 by J rho 2 plus J1 by J rho 1, isn't it? Now, let us see for the drift flux model what the rho mixture or what is the expression of rho mixture that we get. From the drift flux model, we know alpha can be obtained from this particular expression or this particular expression. So, if we substitute this particular expression of alpha in the expression of rho Tp, then we should get the corrected expression of the drift flux, or rather the corrected expression of the mixture density as obtained from the drift flux model. Agreed all of you? So, just substitute and then tell me what is the expression that you are going to get for this particular case. You simply substitute and then you tell me what is the expression that you are going to get for this particular case. Instead of alpha, we can write it down as J2 minus J21 by J into rho 2 plus J1 plus J21 by J into rho 1. Okay. So, we had already defined alpha drift flux as J2 minus J2 1 by J. Similarly, if we define 1 minus alpha drift flux, what is the expression that we will be getting? For 1 minus alpha drift flux, again we can refer to the expressions of J1 there. In this particular case, we had obtained the expression in terms of J2, isn't it? From here we had obtained this particular expression, right. Now, if we express it in terms of J1, then in that case what do we get? Just like J2 equals to alpha J plus J21, in the similar way we can write down J1 equals to 1 minus alpha J minus J21, isn't it? You simply substitute these things and then you find it out, you are going to get this particular expression. From where you get it? We know J1 equals to 1 minus alpha into U1 minus J, right, and we know J12 is nothing but minus J21, isn't it? So, this is equal to 1 minus alpha J1 by 1 minus alpha minus J, correct, or in other words J1 minus 1 minus alpha into J. So, therefore, 1 minus alpha, this is nothing but equal to J1 plus J21 by J. 1 minus alpha is nothing but the liquid hold up HL. Got it? So, therefore, we have derived the expression of 1 minus alpha here, and we have derived the expression of alpha here, okay, alpha equals to this particular expression. Now, if we substitute the expressions of alpha and 1 minus alpha, this expression of alpha which we have got and this expression of 1 minus alpha which we have got in the expressions of rho drift flux, then we are going to get something of this sort, right. Substitute yourself and then you are going to find out that you are going to get something of this sort, isn't it. So, therefore, simplifying this particular expression, what do we get? We get this rho drift flux. Let me write it down again. It was, please do it in your notebooks and then see whether you are getting what I am getting or not. It is very difficult for you to copy these things and then understand them. This will be obtained as say J2 by J rho 2 plus J1 by J rho 1 plus J2 1 by J rho 1 minus rho 2. Yes or no? Yes. Now, what is this particular term? Can you tell me? This particular term, this is rho for homogeneous case, isn't it? I had already written down rho for the homogeneous case, isn't it? So, therefore, we find that this is nothing but rho homogeneous plus J2 1 by J into rho 1 minus rho 2. So, what do we find? We find that for the expression of alpha, we had found that the correction factor was in the terms of a multiplicative term which was a function of J21. And in this particular case, what we find? We find that rho drift flux, it is again a correction factor, it is additive in this particular case, which is again a function of J21, and that additive term when added to the homogeneous value, it gives us the rho drift flux. In the similar way, we can expect to find out U1, we can expect to find out U2, and once we find out U1, U2, we can expect to find out momentum flux and things like that, kinetic energy as obtained from drift flux, the momentum flux as obtained from the drift flux model, we can find out everything. Just try and do U1 and U2 and see how this U1, U2 varies from the homogeneous u1 and u2, or rather the u1 u2 values we had obtained from the homogeneous flow theory. Just do it and let us see what you are going to get. How to express u1? u1, this is equal to, how to express u1? q1 by a1, or in other words in terms of j, very true, w by rho 1 a1 in terms of j, because see what we want to express it in such a way that we can compare the u1 we have obtained from drift flux with the u1 that we have obtained from the homogeneous flow theory. From the homogeneous flow theory, no slip means u1 equals to j1, isn't it? For the homogeneous flow theory, u1 equals to j1. So, in this particular case, what is the expression of u1? Very true, or in other words, is it j1 by 1 minus alpha? q1 by a is equal to j1, fine. So, therefore, this is going to be j1 by 1 minus alpha. 1 minus alpha, the expression I have already derived for 1 minus alpha, this particular expression. Okay. So, you can substitute this particular expression and then you can find out what is the value of u1 in this particular case. Just do it and tell me what is the expression that you are getting. This should be j1 by j1 plus j21 by j, or in other words this is j1 by j by 1 plus j21 by j, yes or no. So, therefore, we know that for the homogeneous flow theory u1 would have been equal to j, agreed, because under that condition for the homogeneous flow condition we get u1 equals to j1 equals to j equals to u2 equals to j2, isn't it? All the two phases they flow at the same velocity, due to which we say that there is no slip between the phases, or in other words k, the slip ratio equals to 1, relative velocity u21 u2 minus u1 equal to 0. So, therefore, u1 equals to u2, and since alpha equals to beta, therefore, u1 equals to j1. So, therefore, u1 equals u2 equals to j1 equals to j2, which gives alpha equal to beta. Okay. From the drift flux model, what do we get? We get u1 is the homogeneous velocity divided by a correction factor, again which is a function of j21. In this case, it is in a slightly different form. j21 by j1 pi. Sorry, j21 by j1, very sorry. Okay. Same way u2, if you try to find out, u2 equals to, here it is going to be slightly congested, I will do it in a different paper. u2, this is equal to again j2 by alpha, isn't it? What is alpha equals to? We have already found out the derivation of alpha, j2 by j 1 minus j2 1 by j2, isn't it? Substitute this value of alpha here, then what do you get? This is j2 by j 1 minus j2 1 by j2, agreed, or in other words again taking up j on the top, we get this as j by j2 minus j2 1 by j2, or in other words this is j by 1 minus, agreed, fine. So, therefore, and under normal circumstances, or sorry, for the homogeneous flow model, so we find this is the homogeneous in situ velocity, okay, homogeneous in situ velocity of phase 2, phase 1, everything is the same. So, with this homogeneous in situ velocity, if this particular correction term is multiplied, then we can get the actual velocity, and definitely it will be a much better approximation of the actual situation. Okay. So, what we have done, first we have tried to see how the drift flux concept it modifies the homogeneous flow theory. What it does, homogeneous flow theory, it assumes u 2 equals u 1 equals to j 1 equals to j 2 equals to j, or in other words this arises from the no slip condition, and from here what we get? We get alpha equals to beta equals to q 2 by everything expressed in terms of input parameters. Fine, but we find that that is grossly erroneous. So, instead of that, if we can introduce something, some particular term which will be a function of the relative motion between the two phases, then we will get a much more accurate value. Okay. How to do it? Now, for doing that, what we have done? We have used the drift flux concept, and using the drift flux concept, what we could do is we could actually modify the expression of alpha, okay, as compared to the expression of alpha which we get from the homogeneous flow theory. Okay. And then we found out that once the expression of alpha and 1 minus alpha were modified, accordingly your mixture density has some particular this mixture density can also be expressed as the homogeneous mixture density added or multiplied by some particular correction term. The local in situ velocities, again they are the homogeneous theory, homogeneous flow velocity added, multiplied, divided by some particular correction term, isn't it? So, from this what do we find? We find that we could actually modify all the parameters that we have decided, or rather that we can define for two phase flow, and these modifications, all of them, they are in terms of the normalized drift flux. Drift flux normalized either with the volumetric flux of phase 1 or with the volumetric flux of phase 2 or with the volumetric flux of the total mixture. So, we have for all the cases that we have done till now, you can try it for the momentum flux, you can try it for the kinetic energy, you will find that for each case the correction term, it is a function of the normalized drift flux, where it is normalized either with respect to the volumetric flux of phase 1 or the volumetric flux of phase 2 or the total volumetric flux. Okay. So, therefore, we find that once we have some particular estimate of J21, where J21 can be estimated from some other equation in a straightforward manner, then that J21 can be substituted in all the equations that we have written down for U2, for U1, whatever equations we have written down. Wherever if we can substitute J21 from some other equation, then in that case once we have an estimate of J21, we can find out all the parameters, or we can modify all the parameters of the homogeneous flow model to account for the relative slip between the phases and to give us a better estimation of the hydrodynamic parameters. If this particular alpha, this particular u, they are substituted in the pressure drop equation, then naturally that pressure drop expression is going to give us a better estimate of the actual situation. Okay. So, now the next step will be how to find out J21. Now, it should normally come from some particular type of a force balance sort of a thing, isn't it? In that particular way, we should be in a position of getting or estimating J21. Now, usually drift flux model, it is very suitable under certain conditions. What are the conditions? When the wall shear is negligible as compared to the interfacial shear. Naturally, because when the wall shear is negligible, only under that condition the interfacial shear will be much more important. Okay. If the interfacial shear is much more important, tau 1 2, if it is much more important, then naturally that arises due to relative motion, therefore drift flux or the J21 comes into picture. Okay. Usually it is applicable for those conditions, it is much more applicable for gravity dominated situations. That means, usually for horizontal flow, as compared to horizontal flow, it is much more appropriate for vertical or near to vertical inclined conduits. Okay. Now, before we go for discussing the how to estimate the drift flux parameter, I would just like to discuss the advantages of the drift flux model. Okay. Now, see, this is just an intermediate. For homogeneous flow, what we had assumed that everything is totally mixed up. So, accordingly we had one continuity equation, one momentum equation, one energy equation for the entire mixture. This is one extreme. Actually, for the two fluid model, if it is a two phase system, we should have a two fluid model. There we should have two continuity equation, two momentum equations, two energy equations, and in these momentum equations and energy equations, the interaction parameters should be included. Now, drift flux model is just an intermediate between the two. It has a mixture continuity, it has a mixture momentum, it has a mixture energy, and it has a maybe a gas phase momentum or continuity equation. So, instead of 6 equations, we have 4 equations here. So, how do we account for this loss of or the simplicity that we have incorporated by reducing 2 equations? We have to supplement it with additional constitutive relationships which will predict J21, isn't it? Now, this is a simplification we are doing. Definitely, it will introduce some amount of inaccuracies. When these inaccuracies are not quite drastic as compared to the advantages it offers, we will definitely go for this model. If it introduces gross inaccuracies, then we will not adopt it. Fortunately, we find that for most of the situations, it is much more advantageous as compared to its disadvantage is one, it is simply an simplified version of the two fluid model, because there are just 4 equations in place of 6 equations in the two fluid model, and therefore, some constitutive equations have to be provided. These constitutive equations, they take into account the actual flow situation, and accordingly these equations are provided. If more or less we have a proper estimate of the constitutive equations, then naturally it gives us much more accurate results and at the cost of much more simplified flow situations. So, let us see under what situations it gives us, or rather under what situations it is much more advantageous. First thing is definitely simplicity, it goes without saying, it is much more simple as compared to the two fluid model. Secondly, it is applicable to a wide range of two phase flow problems of practical interest. Now, remember one thing, see for example, the slug flow pattern, can you call it a completely separated flow model, a completely separated flow pattern, or can you call it a totally mixed flow pattern? It is actually, if you think it logically, it is neither, isn't it? Because if you think it logically, you will find that in the slug flow there are bubbles which are going, these bubbles they move faster than the liquid through which it is flowing. So, definitely there is a relative motion in this particular case, but it is more or less, you can say it is dispersed in the liquid phase. The two phases are not completely separated like they are in stratified or the annular flow patterns. So, therefore, and interestingly this slug flow pattern, it occurs over a very wide range of flow velocities. And more interestingly, see now actually we are going to the era of miniaturization. We are going for smaller and smaller dimension tubes. When we reduce the dimension, interestingly you will find slug flow occurs a much, or rather it occurs over a much wider range of phase velocities. Okay. Now, for this slug flow particularly, neither the homogeneous flow model nor the two fluid model gives a very accurate results. The drift flux model is much better because it takes into account the drift or the relative velocity of the Taylor bubble with respect to the liquid through which it is rising. Same thing happens for the bubbly flow pattern, because whenever we talk of bubbly, it is not always that very fine uniform bubbles are dispersed in the water or the liquid medium. If they are very fine bubbles, the uniformly dispersed, that can occur only under very high phase velocities. Most of the situations what we find, you can even visit my laboratory and you can see there, for the most of the situations it is the water phase and more or less large deformed bubbles are flowing through it. These bubbles, they can be oblate spheroidal, they can be cap shaped, they can be elliptical, but they are more or less defined and discrete bubbles. Now, moment the bubbles they have taken such a particular shape, they will have a relative velocity relative to the liquid through which it is rising. So, naturally under that condition, homogeneous flow model is grossly erroneous. Do you get my point? So, therefore, for the bubbly flow pattern, for the slug flow pattern, for the droplet flow pattern also, droplet flow pattern usually we get it for heated tubes, vapor liquid cases, and this droplet flow pattern they are always said when for the wispy annular cases. There also we find within the gas core there are deformed droplets of liquid. Okay. For such flow situations, we find that the drift flux model, it is extremely advantageous and it is very simple. Simplicity also we have to consider. If it is very complex, if it takes a large amount of computation time, then such models will not serve engineering purposes. Even at the cost of or even at the loss of a small amount of accuracy also, if simplicity and faster computation time can be incorporated, it is going to be much more advantageous. Okay. So, this is number 1. Next thing is fluidized bed also. For fluid particle system, in fluidized bed also we find that all the solid particles they are in a fluidized state, either in the gas phase or in the liquid phase. There also there has to be a relative velocity between the solid and the fluid phase. Whenever there is a relative velocity, if you ignore it and consider homogeneous flow, which we do at times just for the simplicity case, if it gives more or less accurate results, but it does not serve our purpose. So, you will find that for most of the cases, for particularly for the intermittent flow pattern which we had defined in our flow pattern chapter, we find that for most of those intermittent patterns as well as a few of those dispersed patterns which we had discussed, the drift flux model is going to be extremely advantageous. Okay. So, firstly simplicity, secondly it is applicable to a wide range of two-phase flow problems which are practically encountered in industries. This bubbly, slug, drop, fluidized bed, they are actually these things are encountered in industries. Next we find that for rapid solution of unsteady flow problems, pertaining to foam drainage and sedimentation, we find that this gives us a very rapid solution for this. And again, suppose there are instabilities and for the study of system dynamics and instabilities which are caused by low velocity wave propagation, namely maybe a void fraction wave is being propagated. For the study of these things also it is very advantageous. How you will try, you will gradually understand as we go into the details of the drift flux model. Next, see one more thing which is very important which we do. See, in the drift flux model, initially what we have done, we have assumed one dimensional flow only. Okay. Accordingly, what we have assumed that everything varies in the flow direction itself, okay, and there is no variation across the cross section. So, therefore, J1, J2, U1, U2, everything we assumed average over the cross sectional area. But again, this is not a very correct situation, isn't it? So, therefore, we have to consider the variation across the cross section. Now, how do we do that? In the drift flux model, after I have completed the entire derivation part, after I have discussed how to find out J21 alpha etc., then we will see what are the corrections. Corrections also the idea we have taken from single phase flow itself. What are the corrections that has been incorporated to in order to account for the voidage profile, velocity profile etc., etc. Okay. If they are not very drastic, if the corrections are not very much far removed from unity, then they often give very accurate results. So, this is one more thing which drift flux model it offers us. It enables us to account for the 2-dimensional and the 3-dimensional effects. For example, when there are velocity variations, you know, for laminar flow the velocity profile is parabolic. When we go for turbulent flow, we assume a flat velocity profile. Okay. Now, when the velocity profile is parabolic, or when the concentration profile, in this particular case there are 2 phases, say if it is air water phase, most of the cases you will always expect that the air phase does not exist, or it is very less near the wall, because there is always a tendency of the liquid phase to wet the wall. So, naturally there will be a tendency for the gas phase to be concentrated towards the center. So, very frequently we find that voidage profile that also has a parabolic shape like the velocity profile. Now, if this is so, and if you assume that alpha is uniformly distributed over the cross section, and to take that particular alpha, okay, will it give you a very accurate results, or will, considering the actual voidage profile and integrating it accordingly, this particular profile, that will give you a much more accurate results, isn't it? So, the thing is, we do not go into that much complicacy, but we introduce some simple correction factors, again whose idea we have got from single phase flows. So, once we can include what we get an averaged alpha, and then we multiply it by that correction factor. Okay. Correction factor, it just accounts for the rather it just accounts for the fact that it is the property is not uniform across the entire cross section. Okay. If the corrections are not very far removed from unity, we find that the drift flux model, the correction factors which we introduce, they give us more or less accurate results. So, therefore, the next advantage which I have noted it down in the PPT is that it gives us, or it provides us a starting point of the theory to complicated problems of fluid flow at heat transfer, where 2 and 3 dimensional effects across the channel are significant. There also it provides us an accurate correction effects. So, naturally, when it has got so much versatility, quite naturally it is very important and very useful for scaling of systems. Suppose we have performed experiments in a small scale, in a pilot plant scale in the laboratories. Okay, in a laboratory scale, we would like to scale it up for the industrial scales. Okay. So, therefore, if we have some way of accounting for the 2-dimensional, 3-dimensional effects, okay, if we know how alpha can be related with J21, okay, and we know that J21 it depends upon the fluid particle, or rather the fluid interactions rather than the fluid wall interactions. So, therefore, in those particular cases the scaling up becomes very important. This is one more thing. And the other thing, naturally it has been found out that sometimes if we have to do a detailed analysis of the local behavior of each phase, it is probably sometimes much more easy if the mixture responses are known. Is it clear to you? So, in this particular case we have the mixture responses, since we know how the total mixture responds. So, therefore, the detailed analysis of the local behavior of each phase, they can be carried out more easily. So, due to its large amount of application coupled up with its simplicity, the drift flux model is going to be very useful, and we find that for most of the analysis of multiphase systems, a starting point is the drift flux model. It is not the homogeneous flow model. Okay. Definitely, if we go for the 2 fluid model, where we consider the 2 fluids separately, we will be doing this after completing the drift flux model. You will find that the equations are much more complex, you take much more time to solve them, they are much more elaborate, and so naturally we will definitely do it, but you will that time you will feel that well, the drift flux model was a much simpler approximation, and the error introduced as a result of this simplification is not very large. But definitely if you want to use drift flux model for stratified flow, annular flow, you will not get a correct result. Okay. So, therefore, these were the advantages of the drift flux model which I have written them down. These are the different advantages, but remember it is not applicable for all particular situations. For example, it is not suitable for say acoustic. These are slightly difficult things, but we do come across such particular situations in our recent researches, and for these situations it is not at all suitable. One is for acoustic wave propagation, then for the choking phenomenon, and for high frequency instabilities. For such situations it is not at all suitable. Okay. So, therefore, remember one thing, in the drift flux model we have used the drift flux concept, and in this particular case we are having 4 equations. What are the 4 equations? It is the mixture continuity, next is the mixture momentum equation, next is the energy equation, mixture energy equation, and fourth one is the gas continuity equation, assuming that it is a gas phase, or the dispersed phase continuity equation. And what are the equations that we have eliminated? We have eliminated one momentum equation and one energy equation in this particular case. Okay. And since we have eliminated 2 equations, what we need to do is we need to substitute these with additional constitutive equations or dynamic interaction relationships. Means, since we have eliminated these 2, we have definitely considered the relative motion. So, therefore, either we have to give additional constitutive equations or we have to give some dynamic interaction relations replaced by constitutive laws. Now, these particular constitutive equations, they will naturally be in the form of expressing J21 in terms of known parameters. So, this will naturally be our particular approach, okay, that we can, means the constitutive equations or the constitutive laws which will be used, they will naturally be in terms of expressing J21 either as a, in some particular term it has to be expressed, but it has to be expressed in terms of known input parameters. Okay. And remember one thing, the drift flux model is particularly useful when this relative motion can be determined by a few key parameters. It is independent of flow rate of each phase. So, just remember this thing, that the drift flux model, I will just write down this sentence, is quite important. These are the keys by which we go to find out J21. Since finding out J21 is the most important thing here. So, these are the clues by which we find J21. Drift flux model, it is particularly useful when relative motion can be expressed, or rather can be expressed, it is all right, in terms of now how to do this, that we shall be terms of a few key parameters and is independent of this is one particular way by which we can do it. Okay. Now, usually for finding out J21, there are two distinct approaches for finding out this relative motion. Now, the first approach is that we use the mixture field equations and then various constitutive axioms are directly applied to the mixture independent of the two fluid model. This is one thing, we just use the mixture equation and then from some constitutive axioms we just substitute them and we find out J21. The other thing is we use the two fluid model, okay, and then from the two fluid model we try to find out the interaction terms and then substitute them and find out J21. So, in the next class what we are going to do is we are going to discuss what are the advantages and disadvantages of the two approaches, which approach is generally adopted, and then using that approach we will try to find out some particular constitutive equation in order to determine J21. Okay? So, thank you very much.